Welcome to the introductory video of the Triaxial test. This video will include a showcase of the machine, the significance of the test and its use, the sample preparations, the experiment, and finally, applications of the data. In this video, we show state-of-the-art equipment that is used in the faculty. During the lab practical, the bachelor students will use the manual Triaxial equipment. Let us start off by giving a short description of this test. In the Triaxial test, a cylindrical specimen of soil is covered in a rubber membrane and placed in a cell filled with a pressurized fluid. The rubber membrane ensures that the fluid does not interact with the sample, and only pressure is applied. Drainage is provided at the top and bottom plates, allowing water to exit the soil sample if required by the test. Through this duct, pore pressure can be measured and, if allowed, pore water can flow during consolidation and shear. Axial stress is applied by a piston moving through the base of the cell. The piston is driven by an electric motor, and pressure control is provided by a hydraulic actuator. The triaxial setup consists of an electromechanical load frame and a triaxial cell. This 50 kN laboratory load frame provides the resistance and load which is applied to the sample. It can be controlled via standalone keypad operation or via USB interface for computer control. This setup has a cell chamber that can be used for a sample with a diameter of 38 mm or 50 mm. Inside of the cell, there's a 2 kN internal submersible load cell, which measures the axial force applied to the sample. During testing, the sample sits on the sample pedestal, which is fixed to the load frame. 3 feed-through pipes go through the pedestal. 2 feed-throughs are connected to valves with pressure controllers, both being 1 megapascal digital pressure controllers. One of them controls the cell pressure, in other words, the pressure inside the cell and outside the sample, and the other the sample pore pressure, otherwise known as the back pressure. The third feed-through is connected to a pore pressure transducer, which measures the pore pressure in the sample. Another pipe can be connected to the water tank in order to fill the cell. The Triaxial system has a data acquisition system that is connected to the computer. The test protocol, in other words, the test phases and target pressures or displacements required, can be controlled using the computer software. Here, in this video, we will show the steps to perform an unconsolidated, undrained, or UU Triaxial test using a clay specimen. In this test method, the compressive strength of a soil is determined in terms of the total stress. Therefore, the resulting strength depends on the pressure developed in the pore fluid during loading. Furthermore, fluid flow is not permitted from or into the soil specimen as the load is applied. Therefore, the resulting pore pressure and hence strength differs from that developed in the case where drainage can occur. If the test specimens are 100% saturated, consolidation cannot occur when the confining pressure is applied, nor during the shear portion of the test, since drainage is not permitted. Therefore, if several specimens of the same material are tested, and if they are all at approximately the same water content and void ratio when they are tested, they will have approximately the same undrained shear strength. The Moore failure envelope will usually be a horizontal straight line over the entire range of confining stresses applied to the specimens, if the specimens are fully saturated. The specimens are made to be cylindrical. Following the ASTM standard, they have a minimum diameter of 3.3 centimeters. The height-to-diameter ratio lies between 2 and 2.5. The largest particle size should be smaller than 1/6 of the specimen diameter. A thin coating of silicone grease on the vertical surfaces of the cap or base will aid in sealing the membrane. For this test, the specimen diameter is 38 millimeters. The sample is cut to the desired length. We use an undisturbed clay sample, assumed to be saturated. We start setting up the experiment by placing the membrane on the membrane expander, or, if it is to be rolled onto the specimen, place the membrane onto the cap or base. Place the specimen on the base, put the rubber membrane around the specimen, and seal it at the cap and base with O-rings or other seals at each end. With the specimen encased in the rubber membrane, which is sealed to the specimen cap and base and positioned in the chamber, place the chamber in position in the actual loading device. Be careful to align the actual loading device, the actual load measuring device, and the triaxial chamber to prevent the application of a lateral force to the piston during testing. Attach the measurement and control devices and fill the chamber with the confining fluid. Because the actual load measuring device is located inside the chamber, it will not be necessary to correct or compensate for the uplift force acting on the actual loading device or for piston friction. Apply the actual load, which applies a shear stress on the sample. The measurements will be automatically saved in the computer. The final output from the triaxial test are the stage number, the time that has elapsed in seconds, the radial pressure in kilopascal, the radial volume in cubic millimeters, the back pressure in kilopascal, the back volume in cubic millimeters, the load cell in kilonewton, the pore pressure in kilopascal, and the actual displacement in millimeters. Here we plotted some examples of the many different parameters of which we gather data. For example, the graph on the left shows the measured actual load versus the actual displacement. Once the data is obtained from the triaxial test, you can find the shear strength of a soil. An important application for which these properties are needed is determining the stability of dikes, in other words, when the applied shear forces are higher than the strength. An unconsolidated, undrained triaxial strength is applicable to situations where the loads are assumed to take place so rapidly that there is insufficient time for the induced pore water pressure to dissipate and for consolidation to occur during the loading period. On behalf of the geoengineering teaching assistants, thank you for watching.